center of the institution under the aegis of Chemical Engineering Division. Also, it is a great honor for us to pronounce that today we are joined by two eminent panelists and moderator who are authorities on the topic chosen for today's webinar. They will be introduced in the due course. We also have the pleasure to have amongst us the Chairman and Honorary Secretary of Odisha State Center. Thanks to all of you, sir, for being a part of this event. The live telecast of this webinar can be viewed on the National Skill Development Forum YouTube channel, and the link will be shared with you shortly. This is an approved CPD program of IEI, and the link for e-certificate of participation will also be shared with you in the course of the webinar. The Q&A session will commence only after our panelists have finished. The attendees will be on mute and they can post their queries along with their names and designation using the chat option, and these questions will be discussed during the Q&A session after the panelists have finished. Now I will halt my words and start with the program for the day. I'm sanguine your next few hours will be insightful and memorable. Thank you. And now I will request Chairman Odisha State Center, Professor Kirot Kumar Rao, for a brief welcome to our panelists and all others.
Good afternoon, sir. Good afternoon, all of you. So, Honorable President, Engineer Narendra Singh, Mr. S. Rajgopal, Chairman, Chemical Engineering Division, Professor Sapan Bhomik, Chairman CATE, our Honorary Secretary, Professor Dr. Sudhanshu Das, and the panelist, Dr. Tirupati Venkat Pandit, Dr. Shiv Shankar Ayannadi, and Dr. Avinash, moderator, Dr. R. Bhimarao sir. So all the corporate members, students, engineers, ladies and gentlemen. So I am overall extending a hearty welcome to all of you. So first of all, I hearty welcome to our President Ji, Narendra Singh. So S. Rajgopal Ji. So on behalf of Odisha State Center, Bhubaneswar Institute of Engineers, India, I convey my gratitude and thankfulness to all the panelists, Tirupati Venkat Pandit and Shiv Shankar Ji and Avinash Ji. So once again, I hearty welcome to all of you to this webinar. So I hope that I am very much hopeful that today's deliberation will be very much useful and beneficial to our upcoming engineers, students, researchers, those are attending this webinar. Thank you to all. So now I request Dr. R. Bhimarao sir, the moderator, will conduct the webinar. Dr. Bhimarao sir, please.
Thank you very much, Professor Kirot. I am very glad I have been introduced by Professor Kirot, the chairman of the State Center. So the first speaker, Tirupati, is in the hospital because of the heart problem, that is a respiration problem. He is in the hospital in the Bangalore. So we start with the second speaker, Shivkumar Angade. Shivkumar Angade, to introduce him, it is my privilege because I know him from the childhood. Childhood means from the degree college to postgraduate college to PhD to scientist. So this is the first thing I have very privileged to. I am like a father to this Shivkumar and his family. Introduction is required. Professor Dr. Shivkumar Angade, he done MTech Mineral Processing Engineering and PhD from IIT Dhanbad. He has done on graphite beneficiation, potassium kinetics he has done, and his work has gone to column filtration. After PhD completion, he is joined in Tega Industries, Calcutta, where he worked for 2 years and 8 months. He was in charge for the mineral processing laboratory, was responsible for the technical inputs after the selection of the hydrocyclone, Flowsheet development, plant commissioning, conducting plant level test work, improvement of the laboratory facilities, etc. During his tenure, many successful plant commission test works have been carried out since 2007. and he joined in the CSR laboratory, IMT, Bhubaneswar. He is working on the development processing projects for lean grade ores, recovery for critical minerals such as tungsten, rare earths, lithium from Indian deposits. And main research area, Angadi, he visited USA also, a visiting scientist. He was a postdoctoral fellow for the period of 1 year with the Korean Institute of Geosciences and Mineral Resources, South Korea. He has 33 years of 33 peer-reviewed articles, 2 patents, 15 industry-sponsored projects, and 2 years credit. He has guided 4 PhD students on completed, and 3 students are under pursuing. So, may I request Shivakumar Angadi to go ahead with his presentation. Shivakumar Angadi, please.
Sir, Shiv Kumar just called up. The power went off in IMT, so he would be connecting in 1 or 2 minutes. He's just restarting the system.
He has already joined, I think. It's just a matter of seconds.
The topic title is beneficial studies and lithium bearing rocks. We will take up that one. We will narrate about the beneficiation, pre-concentration of the lithium rocks, which will go to metallurgy. Actually, lithium rocks are available. Lithium are not available as main product. Lithium available as a byproduct. So lithium mostly available in the what it is called gneiss and schistose rocks. Lithium mica is available. The mica lithium available in a very low quantity, and where mica is rejected, in that we get as a byproduct. And the gneiss also we get as a byproduct lithium. So this will be 0.01 available in the rocks. Sometimes 0.01 also available in the rocks. That will bring up to 1 to 3 level of the lithium will go at the beneficial studies. Then this rocks will go at the hydrometallurgy process. Like that, he will take up. Shivakumar Angadi will do the talk on that. Shivakumar Angadi, we already introduced about you in your options. You can go ahead with the presentation.
Yeah, good afternoon, sir. Thank you very much for your kind introduction. Sir, there is a technical problem. There is a power cut right now in the institute. I would like to request Dr. Abhilash to start with. I think I'll restore it after him.
Okay. Abhilash, are you ready?
Yeah,
Dr.
no
Abhilash?
problem.
Yeah, please.
I'll introduce about Abhilash.
Yeah, sure, sir.
Dr. Abhilash is a very young dynamic man. I also know him since many times. I have met him many times in NML. Also, IAME, University Engineers Forum, I met him many times. Abhilash is a principal scientist, secondaries and resource cycling group in CSR National Metallurgy Laboratory, India. He is assistant professor, Academy of ACSR is there. He has a doctoral degree in biochemical engineering from Jadavpur University, India. Biohydrometal processing in Indian uranium ores, for which he was awarded Dr. H.J. Arnaka Best PhD Thesis Award from the DIE Government of India. I request Abhilash also to join an IEI Chemical Engineering Division as a member. He is a recipient of several recognitions, namely Fellow of Society of Applied Biotechnology India, Young Scientist Award from DST, INS DIE, and BRSI, Young Metallurgist Award from Minister of Steel and Mines, Government of India, Young Engineer Award by Mineral Engineer Science, and six consecutive Mishra Award in Mineral Bioprocessing, International Mineral Engineers Award. He is a affiliated member of the National Academy of Prestigious Science. He is a member, mentor, and Indian Academy of Sciences, apart from the various national and international professional bodies like IEM, IEMA, MRSI, CRSI, INS, AISM, ISCB, AMA, BRSI. So in this context, I request Abhilash to be member of the IEA Chemical Engineering Division also. Okay, thank you. Abhilash has published more than 90 papers in science SI index journals, national interest journals, and he has got 5 granted patents and 8 already filed patents. He is credited 7 books he published with Tailings publishers in India, and LAP and GM, BH and CRS Plus US edited to the lecture compendium and contributed 12 chapters in the books in the national and international publishers. Area of interest include hydrometallurgy, bioleaching, and waste management, industrial waste, factory scrapping, recycling, exploration bases, process metals, and critical elements. He has guided 35 PhD graduates thesis and guiding on PhD in the field of waste recycling. He is one of the editor board of the international journals and also serves as a reviewer for the specialized journals in his field expertise. He is a project leader for the various projects in the area of waste recycling and utilization sponsored by Government of India and many industry partners. So I request Abhilash, can we go ahead with the presentation?
Thank you, sir. Thank you for the concise introduction and giving. Thank you for Minister of Engineers for giving me an opportunity to share the kind of learnings what we have in the field of. Just 1 second, I'll just switch off my camera because the bandwidth issues are there. So the topic which we went ahead with is achieving sustainability in lithium supply chain via spent battery recycling, indigenous developments and new opportunities. The outline of my presentation would be covering the critical metal scenario in India, the lithium scenario and its criticality vis-a-vis the supply chain. How actually our team deciphers between primary and secondary sources, what are the fruitfulness in secondaries, why lithium and battery recycling is better, and the new opportunities in that. I would like to reinstate that this is a disclaimer to the presentation that this presentation solely belongs to NML Jamshedpur. Anybody who is willing to have more discussions are requested to kindly contact us and avoid taking screenshots or do any recordings. I would start my presentation with the pretext to acknowledge 2 of my supporters in this field and to my prime members, Dr. Pandey, who retired from NML, but who was the one who indulged me in the field of hydrometallurgy, and I'm going ahead with it. And Dr. Pratima, who is very integral part of the lithium and battery recycling activities in NML. And the supporters of CSIR and DSC and the different industrial partners who have partnered us in the past and who have been there in the present. The global, I would start the presentation with the with emphasizing the global demand of critical and strategic metals. Critical and strategic metals are the one which are driving the technological development across the globe. And when we are talking about them in 1700, we had only few metals like lead, zinc, iron, copper, and tin. But as from the time progress in the last 300 years or so, the number of metals have added up, and this adds actually to the kind of gamut of applications which is being covered. And how are these number of metals being supplemented further? It's even this lady will not be able to guess to you that what is the kind of application and the number of metals being added up in this sector. So when we discuss about the critical metals, we should be first knowing about the criticality. This is a critical metals review map for India, where we have taken a selection as the availability of resources, the primary applications, prices, import substitution, and the past expertise. And on this, we can see the zone 1 is the one which has got high economic importance and high supply risk. It is most critical. Zone 2 is moderately critical, and rest ones, the zone actually 3 is least critical. But when we talk about the metals like lithium, it comes on moderately critical because it has got high supply risk. But sometimes the low economic importance has been seen in 2016 when the prices of lithium were low. Now, when you see the global trend in Science magazine 2020, a beautiful article depicting the status, production, and demand of these metals were seen, where the primary metals used in battery production like lithium, cobalt, graphite, nickel, aluminum, copper, and manganese. Lithium was showing a 65% demand in 2050. This is demand of 2050 divided by the production of 2017. So this is a stupendous value which adds to the India's also interest in these lithium-ion batteries, where India have said that we have a 30% EV penetration by 2030, and for this we are starting up the gigawatt power plant, gigawatt factories inside in the country. But you see the lower map globally, we don't have any resource of lithium as such. We don't have resource of critical metals at all, even for the rare earths, except in the secondary resources. I'll skip this. I will just come to the consumption pattern of the minerals. When you see the consumption pattern of the minerals, there are very critical elements have been listed over here, like gallium, nickel, cobalt, lithium, PGM, scandium, and tellurium. These are the metals which are focused to be the somehow available Indian resources. And when you see lithium, the lithium dependency is very high in transport, followed by chemicals and product, and then the metal of lithium for the lithium air batteries. So if you see the cumulative annual growth rate of lithium in transport sector and the chemical sector, this is comparatively similar, going to 5 to 6% annually. This is prepared based on the criticality and the price data of it. And when you see the primary resources available, India has got some spodumene resources in Karnataka, and on which Shiv Kumar has worked, and second resources are primarily available in brine, bittern, and spent lithium-ion batteries. And when you see the current market price of these targeted metals, the target metals of lithium as an oxide, I'm talking about an oxide of lithium as a product, as a powder, it would contain $34 per kg as on May 2020 data of Argus. Because since last 1 year, the data has been reshuffling a lot, and so we have not taken that into account. Now, when I talk about lithium availability in secondary resources, I should give a pretext about the primary resources, because unless and until I am able to justify why I am doing on secondary resources, I will not be able to take my presentation forward. So lithium miners present globally. This is, if you see this data was this is the upper graph is the future perspective, and the lower graph shows you the trend. In 2020, you had the China as 10% available supplier, and Australia was 43.7. But as you move down to 2030, the rest of the world will be occupying the major part of it. And that is the mining production. But when you have the lithium product, because the product is one which matters a lot in this criticality, and lithium carbonate equivalent is the most important feature in this, which actually governs its application in batteries. So when you have Australia, China, Argentina, and Chile as the top suppliers, there are in nations like Zimbabwe, Portugal, Namibia, who are entering in the field by way of extraction of lithium from spodumene, because they have got plenty of spodumene and zinwaldite kind of deposits available with them, which can be a potential source of supplies for the lithium. Now, I'll briefly touch with the lithium supply and mining, because I know Shiv Kumar will be touching a lot on this. But just to give a pre-information regarding the primary resources from where the lithium is being said to be available is brine. Brine is the most common form of lithium extraction. It is salt brine. But it is cheaper, but you need to have a lot of evaporation time, and the startup cost is very high. Followed by spodumene, which contains 0.02 to even 0.65% of lithium inside it as lithium oxide, and you need typical mineral beneficiation process of crushing, roasting, and leaching to get the lithium hydroxide salt. Process is kind of expensive because the grades are low, but it is faster to implement. You have low startup cost because the ore is that friable to have being processed. followed by mechanical brine extraction. Tenova and Bateman collaborated together to set up a plant where they achieved a nearly 90% lithium recovery rate. The plants which are running in Bolivia and Chile have got nearly 68% recovery rate, but this is a very recent development, 2020, where they have got a 90% recovery rate. But it is not yet commercially being established. There are clays available in Jharkhand belt and Bihar belt, which has got spodumene content and has got lithium, but the viability of process gets to be established, and there are institutions who are working on this. So I would give a very blank statement on this, that there is very less potential of currently for India for due to the underexplored or underreported primary resources. As soon as we get more resources, we might be able to do good venturing into it and then start on to work with the primary resources. So when we move from the resources, we have to understand that a life cycle of lithium from mines to battery is very important. How does it come from the mines as brine or spodumene, and then it's get pre-concentrated in the brine as lithium chloride and in the rock as lithium carbonate. So you need to do chemical processing of it. So you get lithium carbonate, hydroxide chloride. That is depending upon what is the kind of acid or the precipitation agent you are using, and you make the precursors, that is lithium carbonate, lithium hydroxide. And then you transfer the matrix stoichiometrically into a battery cathode material, giving you lithium cobalt oxide or manganese oxide or aluminum based material, and finally that comes as a battery. Apart from that, you have got applications in grease and glasses. But if you see on the left hand side the figure, the countries which has got highest finished products over here, China is still leading the race with lithium carbonate, because lithium carbonate is the most integral part in NMC kind of batteries used in Nissan or Honda. The batteries which are used by Tesla are basically having a more ratio of lithium hydroxide rather than lithium carbonate, as published in 2021 Nature magazine, edited by Dr. Harper of LBNL. Now, when we see the primary lithium contribution over here also, the major share, it is from the salars. The salars available in Brazil, Bolivia, and the Triangle nations of South America. So they have got good deposits of that. Apart from that, 27% is being given by different minerals, that is spodumene, zinwaldite, and different micaceous minerals. So it's a big loop chain. If I give you a very simple example published by Roskill, it says that if I'm having a mines in Australia, and then I have to travel all across to Europe to get a very high refined capacity of lithium hydroxide, or the ones in Europe have to fetch a 13,500 kilometers of material from Argentina. The kind of supply chain is very, very high, but this is also a geographical concern, that if you don't have the primary resources, you need to keep on wandering across the globe and found that resources and establish a plant at the site so that it becomes congenial. So the kind of chemistry and the economics have to be worked out a lot. But in case of secondary resources, that is not the situation, because you would be actually having them in your hand. You just need to have a proper collection of them, which is of course difficult, but you can actually do it much better than the primary resources availability. When I see the market and consumption, because when I have the resources, I need to see the market of it. The market of lithium is growing exponentially very well, and the two major factors which actually helps them is the solar panels and the renewable energy and the electric vehicles. And the consumption is maximum in case of the transport, that is 3 C's, consumer, electronic, and computer communications, followed by transport in power motors and heavy duty motors. And there are some good examples, but the consumption is actually split between chemical and technical. So the chemical part is having more values than the technical part of the grease and other applications. So if I go for a table of lithium global market from 2001 on to 2025, there is a 2 times bigger market than the entire what is there today, and you need around a global market of 5,34,000 lithium carbonate equivalent. This value is actually useful more in the electric vehicle. So in 2020, when Benchmark Intelligence made a mapping of the lithium availability and demand, they said that 57% of the global demand of lithium in 2020 was for LIVs, and out of that 65% was for the EVs. So when we have set a target 2030 for India as 30% EVs, so you could actually imagine what is the kind of lithium carbonate requirement coming up in India. So on that pretext, we would still ask you, what is that you would choose? You would choose a scenario 1 where you get lithium as 3 to 7% in the batteries, or you would choose and out of that, if you use 28 tons of lithium from the 28 tons of these batteries, you can make 1 ton of lithium, but you would need 250 tons of spodumene to get 1 ton of lithium, or 750 tons of brine to make 1 ton of lithium. So there is actually a 10 to 30 times of escalation of the factor of the raw material, which actually governs a lot in the economics of the process, and then its availability is a bigger concern. So what we adopted was we went for the secondary sources because we developed a good expertise in the past 8 to 10 years, and it actually suffices the entire SDGs. We can have an affordable energy and a clean one. It can actually support the industry innovation and the startup growth. It would be useful for climate action vis-a-vis responsible material consumption and production. And it would add to 85% less energy and water consumption. It would not give any landfills. That's something which is very, very sure about it. And then no secondary pollutants are there, because hydrometallurgy, actually you might be putting any acid or base, but at the end of the day, if your process has to be economic, you need to recycle everything. And of course, the guys won't be doing this who is sitting like this when you don't have occupational and environmental hazards, because you process the entire battery and get the powder and go ahead with it. So I break the battery over here, and I break the battery into several parts. The main part is the aluminum and the cathode part, where you have the aluminum foil, which contains the cathode in that, and the anode part is the one which contains graphite and some amount of silicon. So the lithium ion battery, if you see a breakup, it contains 47% of the carbon material, followed by highest amount of cobalt and nickel, the most costlier ones, followed by lithium and manganese. It depends upon the manufacturer whether they want to increase the content of all these metals to suffice the cost of production as well as availability of metals. So in 2020-2025, the upper line, we can see a 16.4% of the LIB market being growing on. And this market is governed by the kind of metals available in the market. That's why in 1995, when we were using the toys and all those things, we were seeing the small button cells of nickel cadmium. But at the moment, all the shavers and power tools everywhere, you would be getting lithium-ion batteries only. The market of lithium-ion battery in the orange has actually grown very high as compared to all the other batteries. And the added factor is that the lithium-ion battery or the lithium metal battery, which is coming up shortly, would be having a longer runtime and a good charge density as compared to the other metals like NiMH and NiC. Now, with this advantage of lithium-ion batteries, obviously the demand would be going up. And so demand is maximum available in the light EVs, followed by the mobility sectors like the portable sectors, laptops, mobiles, and all that. And it all depends upon when we have these batteries in their particular chemistry. What chemistry is more in demand? So upper part of demand that battery shows over here that when you have LCOs, the lithium cobalt oxide material, just primitive batteries available, it contains more of cobalt. So the cobalt consumption was very high, and then the resources of cobalt are very, very scanty. Actually, India doesn't have any resource of cobalt altogether. Of course, we don't have for lithium as well, but at least it is better than the cobalt scenario. And then when we move to the nickel cobalt aluminum, which is used by Tesla, it is actually governed by the nickel, but nickel is also a very, very critical metal. And the below graph, if you see, the lithium NMC cathode, that is the nickel manganese cobalt cathode, it actually has overtaken all the other chemistries in the recent past, and it is bound to do, because the charge density and the reliability of these batteries are more than the LFP batteries primarily and the LCO batteries. So if you're able to have a 1:1:1 ratio of lithium nickel cobalt manganese, which is categorically not possible, you can actually substitute by increasing the nickel and manganese concentration and decrease the concentration of cobalt, and this would actually helpful. In the forthcoming slides, you will come to know what is the kind of role of each metal in these batteries. Now I would come from the chemistry to the market balance, because if I have more cathode, what is the kind of sales for me? So the value of lithium in the electric vehicle sold globally, you can see the kind of rise in January 2020 pre-COVID situation. The post-COVID data are not very clearly available, but if you see the forecasts of Bloomberg, it clearly shows you the battery demand in 2020 vis-a-vis the actual cost of batteries. The cost of batteries is currently very high. It stands at nearly $400. But if you go down the scale, to 2030, the kind of cost of batteries will go down because you would be able to suffice more of lithium from the secondary materials, that is batteries. So it will be easier to recycle the entire stuff. Now, this is a table I was talking about when you have a primary resources and what is the kind of criticality they play. The lithium actually gives a very important characteristic to the battery is that it's a low weight material. The atomic number is 3, so it's a low weight thing, and the electrochemical reactivity is very quick. You have 3 ions to keep on moving, so that is the important part of lithium. Now, cobalt, though it is very scanty, Congo is the biggest producer of this, but it doesn't extract out cobalt. So what it is done is that the 80 to 90% of cobalt which is being mined in Congo is being transported to China, and then China makes the cobalt and sell it to all of us. So that's how China becomes the largest exporter of cobalt and the largest importer of unrefined cobalt from DRC. So cobalt, it does is that it gives a very high thermal stability and energy density. So as soon as the lithium and the cobalt is taken up, you have nickel. So nickel and cobalt contribute to the energy density and storage capacity, followed by manganese, which has got assistance of the electrochemical behavior. And the manganese is very cheap. You know, India has got good amount of manganese, and still we have the largest importer of manganese, but still we have got the 6th largest reserves of manganese in India. MOL is a big company, and they are in the process of making good amount of CMD and EMD for battery making with some of the technologies of CSIR, of course. And the last one, India ranks 3rd worldwide in graphite, but we are not able to use this graphite resources for battery making. At the moment, people are talking of only lithium carbon based capacitors, where the graphite would be playing a very good role. So this graphite resource and even the recycled batteries could be a very good resource for making these capacitors. So this actually opens up the battery race. Everybody runs in this race because who contributes more leads the market of EVs as well. So China is the one after 2013 leading the entire market, and is expected to supply nearly 60% of EVs and the raw material by 2030. So in 2021 to 2029, if you see, the demand of nickel will actually double, cobalt will go 3 times, and manganese and flake graphite will go 4 times, and lithium actually will go 6x times. So this particular webinar focus on lithium actually gives you the entire flavor of how does the demand of lithium grows and how are you able to connect the theme of the seminar. So this is something which we have discussed already, so I'll leave it. Yeah, this is a beautiful picture which gives you a global EV dominance. Out of a recent webinar which I attended with the European Union and the raw material section, and they have a very good ET seminars going on every month where they show up the kind of EV penetration. And if you see, the ones in the blue at the bottom is somewhere where we are located: Chennai, Kolkata, Hyderabad, Mumbai, Bangalore. So our EV penetration is quite less. And the ones at the top, the Norway, Oslo, and the countries like Netherlands and all, they have got a very high EV penetration. So we are still catching up, but I'm sure the kind of aim that we have in the current scenario in India, and the kind of penetration we are keeping up to 2030, this graph is bound to change in next 5 years. But how much lithium do you have in secondaries? Because you know about primaries. If you see a Tesla vehicle, Tesla model 7542 has got 51 kg of lithium inside it. 51 kg of lithium in a car is a value which is like, you don't have to worry about the mines at all. Other vehicles like BEV and HEV has got 10 to 63 kgs. The Tesla Powerwall, which is being put up with the Tesla spaceflight, also has got 10 kg of lithium inside it. Now the power tool batteries, the Bosch batteries, which Bosch tools which we are using, has got 100 grams approximately batteries, and then it contains laptop batteries, smartphones. So everywhere the kind of material which is available is somehow more than the primary resources available in the market. I'm not trying to discourage the primary resources like Shiv Kumar, but he knows the fact of it that the lithium is tremendously available in secondaries as compared to primaries. So when you have, I'll give you 2 scenarios over here in smartphones and mobility. One is smartphones, where if you see the graph over here on the feature phones and multimedia phones, India has got a very big occupancy in the feature phones, 80%, and 60%, 66% in the multimedia phones. And this is where we are actually doubling our requirement of phones, and that's how the battery requirement goes up. And at the end of the day, what you do is this guy is using with one mobile phone and throwing up the other, so the waste gets accumulated. So this waste becomes a potential target for various metals. Here you have got rare earths, you have got critical metals, you have got precious metals, and more specifically lithium. So if I give you a basic breakdown that National Institute of Advanced Sciences India published in 2013, they said that if you are able to recycle 150 billion numbers of phone, 150 billion numbers of phone, so it would be contain all these 15 metals, and it would give me 60 tons of lithium. 60 tons of lithium would be actually a scenario of mapping a mineral resource. So this was a very good figure which I thought of sharing with you people, that the kind of batteries which you use in your mobile phones, if you are thinking that it is not useful, so you should be having a responsible recycling of it. Now, when I produce the metal ions, I should be talking about the environmental aspects also. The upper graph gives a good scenario about the German brines, the American brines, the Chilean brines, Argentinian brines, the 4 triangle nations coming up, and the Australian spodumene. So this gives you the scenario that when you have a situation of 5 ton carbon dioxide consumption per ton of lithium hydroxide that happens in Germany, you have got nearly 15 tons of CO2 consumption per ton of lithium hydroxide happening in Australia. So for producing 1 ton of battery material by mining, followed by concentration and refining, you actually make 10 tons of CO2 for lithium, 42 tons of CO2 for cobalt, and nearly 8 to 9 tons for manganese and nickel. This is what would definitely contribute to the GSGs. Of course, India will not be playing a role in this at this moment, but we might be definitely thinking about this, and these numbers of India might be changing the Paris Agreement. So when I move on to the cathode materials from the production of lithium hydroxide, primarily, as I gave you earlier, that we were having LCOs in the primitive ages of 1 or 2 people who were having the mobile phones. At least 1991, I never had a mobile phone, but 2007-8 I definitely had, and I don't know exactly what chemistry was available at that time. But here it shows a very, very good idea that in 2007 post, you have got NMC 662. 662 actually gives you the ratio of nickel, manganese, and cobalt inside it as compared to 811, where you have a lower content of cobalt. And the reason is that people have shifted from NMC 111 to 811 is that nickel actually helps in increasing charge density, whereas at that time the cost of nickel was very low. But at that time, at present, the cost of nickel is very high. So if I split the entire cell, a battery cell, into different forms, I get to know is that my cathode material, which contains of nickel, lithium, cobalt, and manganese, actually is the 72% weight of the entire battery, the cost weight of the entire battery. So that is where the money lies, and that is where actually all the people who are working in the extraction of metals from batteries focus on to. And when you focus on to, you need to get the raw material. And where to get the raw material? In 2020 to 21, you can see the maximum raw material sector is the consumer electronics. You have the laptops and some of the batteries. But as the situation goes forward 2030, the 80% of the market capture of the is from EVs. So all the batteries you would get primarily would be from the EVs, and they, as you know, has got 10 to 60 kgs of batteries inside it. So this would be a very, very good raw material to go ahead with the lithium extraction. And here also, if you see, the transportation sector is in orange, which contributes maximum to this. And a very good statement by the CEO of Honda in 2020, where they said that the total value of the critical metals available in Japan for a vehicle production is predicted to reach about $936 in 2035, where $325 million would actually be contributed from the ELVs. So they are making around 35% of their demand from the batteries for their own new battery production. So this is what actually is the need of, or that you have to think about circular economy, and then conservation of the secondary resources and less scanty primary resources. So this has got potential. If I describe the cost of it, cobalt is the most costly, followed by some of the metals. But here I show you 23rd April 2021 LME data, which gives you nickel slightly ahead of the race with cobalt, followed by lithium, cobalt, and lithium carbonate. And Volkswagen Motors, which I visited somewhere in 2019, had a very beautiful plant coming up for EV batteries. And their recent subscribed articles shows that they have done an assessment of 1.7 million tons of batteries. And they say with at least 80% of recycling and 10 years battery use, they would be able to make 250 tons of active materials. This actually gives you yearly 20 to 30% of European demand. So this is only for 250 tons for 10 years battery use. So you can see a 20 years back the line, what is the kind of this demand is going up. So everybody is thinking about recycling, and that's how recycling has to be there. Still, when we have only 1% recycling occurring in the actual scenario. So when you do recycling, you have to have an assessment of total recoverable metals. It was very low. At the moment is very low, but when you add on to this figure to the current research and the commercial aspects and the transport scenario going on, you can see over here the maximum contribution, of course, is from the nickel part, because nickel prices will go up, followed by cobalt and lithium. That is the LCE equivalent over here, is able to give you 10% of the total demand 2025 if you are able to have the substantial quantity of batteries being recycled. So every time stressing upon this is because this is a figure taken from LI cycle, because when they say that they are producing all the metals, they're also assessing the total recoverable metals for the next 20 to 30 years, and they also assess the environmental comparison. This is a very good scenario. If you see, mining and refining gives you 6.78 tons of CO2 emissions and nearly 1 ton of NOx and SOx emissions, whereas the CO2 emissions by recycling is only 1.75 tons, and the water consumption is nearly 30 times less. So if you are thinking about mining and refining of lithium resources and going ahead with the low grade materials, you actually give a thought about the secondary resources as well. And that is why we have got nearly 80 to 90 companies coming up in India already established on thinking on these aspects, and some of which who are already contacted NML for the technology agreements and technology transfers. Before we give what actually Indian scenario is, we would like to give you a scenario about what others have done. Toxco, based in US, are using the lithium-ion batteries by dismantling method. They make lithium carbonate, but they don't make other metal ions. Similarly, recoverable in France, they take LCO batteries, that is lithium and cobalt batteries, and they make cobalt oxide, hydroxide, and lithium carbonate. But these processes may not be are not viable in the long run when you have a mixed battery system. And one of our reviews, which published that Umicore also makes nickel and cobalt rounds, but the most important thing over here is that they lose the lithium in the slag. So sorry about this. It's an automatic movement in the slides. And Accurate Germany also does the same thing. They are making alloys. So you're not getting pure metal to make batteries. Now that's why when India CEO Amitabh Kant of Niti Aayog, he said that when we are moving to low carbon emission, we should be thinking about lithium-ion batteries. And nothing wrong in that when we are thinking on this, because there are 15 companies in this race already in 2020 in the FAME race, that is fast adoption of hybrid electric vehicles, and they are preparing together with India's roadmap of 50 gigawatt hour plant. You must be aware about the plant coming up in Sikri Karaikudi, where they're making lithium-ion batteries which are indigenous, but it could actually be due to the supply of raw materials from outside or even purchase. So lithium-ion battery recycling could actually help in sufficing the raw materials in India, and the supply chain can be closed. Now I would try to give a very good difference about lithium-ion battery and lead-acid batteries. People say that lead-acid batteries are doing the same job of EVs, and they are less costly, and you should actually go for it. I'll give you a scenario. Yes, the lead-acid batteries actually are weighing 20,000 crores, and is going still stupendously in our bikes and autos and all. But if you are able to replace them, you would actually need 1 million ton of electrode material. In Jamshedpur, at least, we have been knowing that the diesel autos have been stopped, and people have been asked to move on to CNGs or gasoline-based autos. So time would be soon that you would need also to move to battery-based materials. And here you can see in 2011, the lithium-ion battery cost factor was very high as compared to lead-acid batteries. But 2020, we are closely matching up, reading 1 to 1 is to 1.5, and it would definitely come down as soon as the lithium production starts from the recycled batteries. This factor is bound to go lower to the LABs. So we should be thinking about end of life battery recycling, and we should be having a very segregated method of collection of them, dismantling, and followed by recycled metals. And this would actually open the way for the 3 R's, that the reuse, remanufacture, and recycle, because that's an imperative need of the hour, because what you throw has to come back to you itself at one day. And based on this, there is a clear differentiation of process routes. This flow sheet was published in one of our papers where we tried to show the differences between pyrometallurgy of lithium-ion battery recycling vis-a-vis the hydrometallurgy. And in pyrometallurgy, if you can see, we are losing out lithium, but we are making all the other metals as alloys. But in hydrometallurgy, you are able to get each metal separated out as electrode powder, and it goes actually into a saleable product. And it is working with ambient temperature. So it is actually very useful. The boon, it's a sensible choice, and the critical metals in the batteries can be recovered. You can make huge money out of it. The bane is, of course, yes, you must have read in papers and in magazines and TV articles that the mobile phones have bursted and all that. Yes, it happens, because if you are aware about what is happening with your mobile phone, you will not be able to suffer those things. But when they burst, they cause good amount of toxic and highly flammable gases to come outside, and they are toxic. So when you dismantle these batteries, you have to be doubly careful that these batteries have to be dismantled properly, so that you avoid the risk of explosion and don't contaminate the soil or groundwater. Based on this, people started the research work on mobile phone batteries. Very easy to dismantle. I won't say very easy, but it dismantles very easily. Then the laptop batteries. Below you can see how did Pratima during her PhD dismantle the laptop batteries into the cells, and the cells into the various fractions as copper foils and aluminum foils. The copper one gives you the graphite, the aluminum one also gives you the carbon, but this black coating on the aluminum foil actually is the money on this. It contains lithium, nickel, cobalt, and manganese. So when your battery fluffs or it swells up like this, as in the figure in the red circle, you actually are supposed to do the recycling of this, and that's where the recycling of batteries or mechanics step has to be there. So why NML is the first and the pioneer laboratory in battery recycling in India is that we are the one who have published more than 40 papers in the last 10 years in this, and we operated the first project of battery recycling in 2010. In case of EV battery recycling, when Nissan came to CSIR, it went to IMT and NML, and fortunately our technology was taken as a patent, disappearing any of the contentions. And at the moment, we have developed the transfer technologies to 4 to 5 industries who, for recovering cobalt from the batteries. And in this particular scenario, in the last two financial years, we are working on development of new flow sheets for recovering of all metals. And I'm happy to share that we have developed this flow sheet for extraction of all metals from the lithium-ion batteries on a demonstrable kind of scale. So this was the actual scenario a few years back, but at this moment we are coming up with a 100 kg pilot plant input, where we are getting more variants of this by solvent extraction, and more purity and more inputs for the fresh battery making. And of course, the copper powder gets made as a copper foil gets converted into copper powder, for which we also have a patent. Then we have made this flow sheet which I was talking about, a flow sheet which is completely sustainable. With the theme of the presentation that we grind the battery, separate the powder. This is by manual separation. We take the powders and do the leaching of it. By 3-stage solvent extraction, we make manganese, cobalt, nickel, and lithium product in different forms, and then the acid is recycled back, and then the carbon is made as graphene. And this process has been patented by NML. So we compare ourselves with the rest of the world is that we have companies from Belgium ranging to Canada, and they are being able to recycle different type of batteries by pyrohydro method, but very few of them have got the technologies to make all the metals out. But the companies who come to us for technology, they always say that ki bahar ki technology bahut costly, it contains 70 to 80 lakhs. But what we offer in NML is a relatively cheaper technology and relatively sustainable, because we are working on a mixed chemistry of batteries by mechanical hydroprocessing to make all these metals under a CSIR mission project. And here I would like to give you a very brief idea about the kind of economics. If you have 100 kg of laptop batteries, which is give you 25 kg of the black powder, it will give me 5.7 kg of cobalt, nearly 1 kg of lithium, 0.5 kg of nickel carbonate, and manganese carbonate 5 kgs. And the end of the day, my economics is that on a global average of 8.85 profit, we are able to have a cost calculation in Jamshedpur for free or very less quantity of LIV, a 20% profit margin with expected sale of 188 lakhs for 1 ton of 100 kg of battery being processed. So this is the kind of the plant which we are coming up in NML for 100 kg, where we'll be at the end of the day we'll be teaming up with Sikri Karaikudi for the powder and the battery fabrication. In EV, like I mentioned, I can show only one slide about it, that NML worked on EV for selectively regenerating the cathode material, and for which we have a patent with Renault Nissan and Nissan in India. So once we are done with the batteries, we should also know one thing is that our cars are costly nowadays because of many things. This seminar is focused on lithium, but I would like to draw your attention to different metals as well, that these metals would be required in high quantity in the cars, like gallium. You have your motors containing rare earths, and your machine tools containing rare earths, and your catalyst contains palladium and platinum, which are the rarest of the rare metals available in the earth crust. This is a picture from Professor Mikia Tanaka of AIS Japan, which he presented in TMS last year. This is a slide we drawn from Professor Animesh Jha, who presented a lecture on at the Vaibhav of India, and he showed that what is the kind of requirement of the rare earths in the different bat and different car components. And if you see over here, for an average hybrid vehicle, you would require nearly 1 kg of neodymium, which costs you 1 gram costs you $42. So that is the kind of scenario. And windscreen catalytic converter, like I explained, you have hot metals. Summary of NML contributions in this on industry interface, that we have executed more than 15 projects. It's actually 22 at this moment, but I'm going only with the numbers which are completed. We have 10 technology transfers and demonstrations given with nearly 12 IPRs generated. Nearly 6 PhDs have come up, and publications of 40. This is actually sheer lowest total. We don't want to disclose other numbers, which we can't actually do it. Conclusions is a time for fundamental changes. We need to demand of the lithium would go up, so we have to keep our eyes open that we should be choosing the primary or secondary, and if we're choosing secondary, we should be seeing what kind of raw material should be processed, and we should be coming up with interdisciplinary routes for multi-institutional kind of activities, where a lot of lithium which is available in the secondary sources needs to be explored. So we should be doing it together as much as we can, and we should be ready to tackle. Thank you so much. I thank you, IIE and Dr. Bhima Rao and Tanmay, to give us a chance to exhibit NML in the virtual mode and present what we have done in the past 10 years for a sustainable flow sheet development. Thank you so much.
Thank you, Abhilash. Chakravarti sir, Tanmay.
Yes, sir.
So I
We have already transferred the presentation right to Dr. Shiva Kumar. I think he can now present, sir.
okay.
Yeah, good afternoon, sir. Is it audible?
Audible.
Yeah, thank you very much, IEI, for giving me an opportunity to speak on our small work in the recovery of lithium from the primary resources of India. I would like to thank Dr. Bhimara also for his initiation in this activity. And yeah, in fact, I'm thankful to Dr. Abhilash also for his I mean, you made my job easy. Actually, already introduced about the uh, most of the aspects of lithium usage. Yeah, actually, we started working on this lithium for the past 1.5 years. Uh, so my presentation contains introduction and the demand and uses of lithium, production, the distribution of lithium bearing pegmatite and brine deposits. And with respect to Indian deposits, I mean, where are the lithium occurrences and how much is their quality? Uh, that information will be available with this, and the typical process of flow sheets for the production of lithium carbonate and research what we are carrying out at IMMT, and some of the beneficiation practices worldwide. That information also it has. The disclaimer is the contents of the presentation are a summary of our work, and it should not be considered as the complete information. And I request the presentation slides need not be copied in any form. Well, as Dr. Abhilash already introduced about the lithium, I'm just going through some of the slides. It is a very light alkali metal having atomic number of 3 and atomic weight is 6.94. Density is 0.534 grams per cm cube, and yeah, uh, the abundance of lithium in the elemental, say, earth crust, continental crust is about 20 to 70 ppm. The uses of lithium, you are already aware. It is basically used as a flux in the silica processing, and recently the importance of lithium increased like anything due to the applications of lithium ion battery. These batteries, they can generate 3 volts per cell, so that is much higher compared to lead acid battery and zinc carbon batteries. And the lithium also have applications in the high temperature lubricating greases. Well, some of the minerals what we use for the extraction are listed here. Spodumene is it is contributing largely, for the extraction of lithium, and which is aluminosilicate, and followed by spodumene petalite, lepidolite are another two important lithium bearing minerals. You can see other minerals like Mb clonite and eucryptite, etc., are also available in the earth crust. The theoretical lithium content in the spodumene is almost about 8.1. In the sense, in case we can have a clear spodumene crystal, we'll be having lithium content in that spodumene will be about 8.1. And yeah, this is a theoretical value, and however, actually in practice about 4.5 to 8 percentage will be available actually. And with respect to petalite, the actual lithium content will be 2 to 4, and in lepidolite, of course, it is 1.2 to about 5.9% actually it can be found in the ores. The lithium is produced either from brines or minerals. I hope Dr. Abhilash has already explained about what are brines and the other resources. In the year 2020, about 56 percentage of the world's output was from the brines, and about only 44 percentage was produced from the minerals. The brines are almost, yeah, they are low cost on an operating basis, but development of the brines project, it takes a longer time, and vis-a-vis with respect to the development of projects on minerals, it takes 3 to 4 years time. Well, with this small introduction on the lithium, I would like to go ahead with the production status. Lithium is basically available in the granitic uh, pegmatites. So along with these pegmatite rocks, a lot of other valuables will be associated, which we'll be speaking later. And with respect to recovery of lithium is concerned, spodumene, petalite, and lepidolite are, yeah, they are mined commercially. And spodumene, amongst all of them, spodumene is containing the higher lithium content, which is about 8 percentage. And yeah, on an average, the deposits, suppose containing the spodumene, uh, which is 12 to 20 percentage spodumene, it will be assaying about 1 to 1.5 percentage of Li2O content. So in case the deposit or the ore sample containing 1 to 1.5 percentage, it can be treated as a lithium ore. The first step is to do the concentration following the mineral processing technique, and the objective is to remove the unwanted the gangue minerals out of it. By doing that, we'll be increasing the lithium content, and the commercial concentrates of these spodumene or lepidolite or whatever it is. So it should have something about 4 to 7.75% Li2O contents, which can be subjected to hydrometallurgical extraction studies. Well, this is about small information about how the lithium demand has been increased from 2009 onwards. You can see the first circle where the lithium ion batteries, they were having about 18% demand. In the year 2014, it has been increased to 35 percentage, and in the year 2019 it is increased to 56 percentage, and in 2024 it is increased to 61. So you can clearly see the increase in the demand for lithium ion batteries has uh, driven the production of lithium worldwide. Lithium demand is expected to increase again by 2024, especially because of EV vehicles, as Dr. Abhilash already informed. And the lithium market is expected to grow 184,000 tons per annum of lithium carbonate to 534,000 tons per annum by 2025. Well, the production of lithium worldwide, it shows here. You can see the mine production. It is exclusively for the hard rock deposits. It is not considered the brines and the recycling activity. In the year 2019, about 86,000 tons of ore, lithium, is produced. And you can see Argentina, United States, Argentina, Australia, Brazil, Canada, and Chile. The production from Australia is accounting something about 52.3 percentage, followed by Chile about 22.4 percentage, and China is the third amongst that, 12.5 percentage. Well, here is a small information about the occurrence of pegmatite deposits all over the world. You can see the deposits are scattered all over the world. Mainly in the Australian continent, you will have the pegmatite deposits that are containing spodumene, and followed by that you will be having in the European continent also spodumene occurrence is there, and in the American continent also it is occurring. The interesting fact is the Afghanistan is having one of the biggest resource of spodumene, and yeah, almost everybody is having eye on Afghanistan right now, and of course it will be considered as similar to what oil was having in the Arabian countries. So slowly the importance of oil in the Arabian countries is going down, and I'm sure within shortly everybody will be after the resources what Afghanistan is having. And yeah, this is some information about these deposits of lithium. You can see here in the Australian continent, green bushes. That deposit is having about 118 million ton of resources, and it is assaying 2.4 percentage of Li2 content. And almost say in the Australia, it has been mapped, and almost you can find it in the table. In the Canada and yeah, Spain, you can see the quality of the ore is bit inferior, but nevertheless, yeah, the quality 0.6 Li2O content to about 2.4, it can be used for the extraction of lithium. A few examples of the brines around the world you can see here. It is mainly restricted to the South American continent. Argentina and Chile are, yeah, you can see the brine extraction of lithium from the brines are taking place in the Chile and Argentina. And in the United States also some brines are there that is containing lithium, especially in the Utah and in Nevada and California. Lakes are there which is containing lithium. Well, this is what the production of lithium from brines and the pegmatite it appears. The spodumene concentrates are being generated, and mainly it is exported to China. You can see the requirement of United States were mainly met from Chile and Argentina, and of course China is importing from Australia as well as Chile and Argentina. And you can see from Australia about 58,000 tons are produced in the year 2019, which is mainly the spodumene concentrate. But when it comes to the Argentina, it is the brine, and it is in the form of a lithium carbonate and chlorides. And here, with respect to Chile, about 62,000 tons were produced, mainly in the form of lithium carbonate and hydroxide and chloride. Well, this is a slight information on the lithium production cost. The brines production cost will be a bit higher in terms of yeah, these entities like labor, energy, reagents, and so many other parameters. It will be containing something about $5,500 per ton, and vis-a-vis the hard rock, it will be having a production cost of about $2,500 per ton. And here is the cost of the concentrates, what we generate. Say, suppose the hydroxides will be costing the fetching the market price of about $17,000 per ton of lithium carbonate equivalent, and the carbonate, say lithium carbonate concentrate, will be having the price of about $11,000, and chlorides will be having about 10 to $10,200, something like that. The concentrates, the lithium concentrate after beneficiation, what we are going to generate will be fetching something about $5,000 per ton. Well, these are some of the occurrences of lithium in the Indian continent. It is already reported from GSI studies, and here are the spodumene occurrences in the Karnataka. Amareshwar deposit is located north of Karnataka, and which is having a lithium content of about 2.12% on an average it is. And other deposits are say especially the Bastar district in Chhattisgarh is containing lepidolite, and maximum lithium content what it is showing in the literature is 3.34 percentage, and in the state of Odisha it is containing in the Koraput district, and it is a bit inferior in lithium content, which is having 0.25 to 0.8% Li2 content. And recently we started working on this Bihar Mecca belt, which is containing lithium content varying between 0.4 to 3.35 percentage. And of course, actually in the northeast region also it has some occurrence. Actually, yeah, most of these occurrences are in the forest area and associated with the pegmatite occurrence. Of course, actually, everyone has some doubt whether we can able to explore the Indian uh, deposits or no, because we don't have a complete information about the geological occurrence or the exploration data available with us. You can see the figure where G1, G2, G3, G4, it stands for the geological information. G1 is the highest information what we'll be having about the deposit, and G4 is the least information what we have. And you will be having in the z-axis the feasibility information. F1 is having the complete information about the project, and F2, F3, F4 is the least information, in the sense we don't have much information about whether technically it is feasible or no. And in the y-axis you will be having the socio-economic viability information. Again, here E1 is the, say, highest socio-economic information, E2 is the least, and of course E3 is the least, and E2 is in between. We can say technically, or the commercial projects are one which has the complete information like 111, but in reality will not be able to get this 111 information instantly. So in many times we travel diagonally. So in case we have G4 information, those projects are also can be commercially exploited. And in fact, in many cases, this diagonal path is chosen. So considering this concept, we can think of the Indian deposits has some potential, and we can do some more work on that, especially on the exploration. Here is about our activities, what we have carried out, and on the right hand side you will find Mr. Tanmay Kundu, who is working for his PhD on recovery of lithium from the hard rock deposits of India. And yeah, we started working on spodumene occurrences of Karnataka. We visited the field. You can see the exposure of the pegmatite rocks in the field. Yeah, we collected the samples at different locations, and the chemical composition of that rock is shown here. It is mainly containing these silicates. About 71.4% is silica, alumina is about 16.19, sodium and potassium contents are varying here like this, and lithium content Li2O is varying between 0.2 to 0.6. Of course, actually we were not having much exposure, and in fact actually it requires some more uh, exploration facilities to go into deep about the uh, sample collection. With the existing information, say the sample is mainly containing the spodumene. The lithium bearing mineral is the spodumene, and it contains quartz, plesioclase, potash feldspar, muscovite, and garnet. Well, uh, this is what the chemical composition of the samples what we have collected. Li2 content is about 1.1, and other constituents are as shown here. Well, we subjected the material to the crushing. Comminution studies have been carried out, and subjected to the size analysis. You can see in the table, first column it shows the sizes, and the second column it shows the weight percentage retained on each size, and the third column it shows the Li content, and the fourth one is the Li2O content of these each size fractions. And you can see the lithium content in the core size it will be a bit higher compared to the ultrafine size, especially 45 microns, and that is not containing much Li content, Li2O content. The coarse fraction will be having more Li content. So what we have done, we subjected the sample to the sink and float studies, and here what the results are. You can see the second column is again the weight percentage, and the lithium content, and the fourth column is the distribution of lithium amongst the size fractions. You will find here the intermediate size, especially in the size range of around 500 to 75, it will be having a maximum distribution of lithium content. Well, each size fraction has been subjected to sink and float. You will find in the columns like sink and float, the sink fractions will be go on decreasing, and the float fraction is yeah, go on increasing with respect to particle size. On an average, we can able to say that in case we subject the entire material to the density of about 2.89, or what we call as a bromoform, the sink fraction will be having the weight percentage of about 21.3 percentage, and the float will be having about 78.7, and these heavier fractions will be carrying the spodumene. It will be saying about 4. Well, these sink and float fractions we subjected to again scanning electron microscopy. You can see beautiful crystals of spodumene have been enriched in the sink fraction. The dumbbell-shaped particles you will find here, yeah, they are the spodumene particles, and the feed was having some irregular particles along with the spodumene. You can see the density fraction greater than 2.89 is having uh, spodumene, and the density fraction lighter than 2.89 is having some silicates. Well, again, we extended that activity, and I would like to mention one of our colleague, Dr. Nilima Das. She could able to do some of the characterization studies here, and these area 1, area 2, 3, 4 have been mapped, and it shows that the first particle, what is shown here, is a spodumene, and the second one is a feldspar, irregular shaped particle. It is a feldspar, and again third and fourth particles are spodumene contents. Well, we subjected the sample to different gravity concentrators, and of course, actually the coarse size we subjected to the Wilflet table, and the fines fractions we have subjected to advanced gravity concentrators such as Nelson concentrator and Falcon concentrators. It shows that the lithium content, it can be enriched to about 4 from the feed containing about 0.6 to 1% lithium. It will be enriched to about 4. And we have carried out a couple of flotation studies. You can see we have done some direct flotation as well as the reverse flotation. The direct flotation is the one where this spodumene will be concentrated in the froth product, and of course, actually the reverse flotation is the one where the spodumene will be enriched in the non-froth, and the silicates will be floated. You can see experiment number 2. The concentrate is enriched in lithium contents above 5%. So the flotation and the gravity concentration, etc., are extensively used, and it shows that it is possible to enrich the lithium content from the Indian deposits. Finally, we have developed a flow sheet which is consisting of the comminution circuit to reduce the particle size, and subjected it to the primary and secondary crushers, followed by ball mill, and hydrocyclones. They were operated in closed circuit. The cyclone overflow will be subjected to advanced gravity concentrator, and the gravity tailings will not contain the lithium content. The heavy fraction containing lithium values will be further subjected to very high intensity magnetic separator, where the magnetic impurities we are planning to remove it, and the non-magnetic fraction has been subjected to the flotation studies. In the flotation, we enriched the spodumene concentrate, the lithium concentrate. This spodumene concentrate is subjected further to the hydrometallurgical route for the extraction of lithium in the form of lithium carbonate. Well, these are some of the extraction of lithium from spodumene available in the literature. These are some of the pyrometallurgical routes: sulfation, carbonation, chlorination, fluorination, etc. are being used, and yeah, it will be roasted at different temperatures, and of course the roasting temperature, etc., will be maintained. Temperature and time will be maintained, and followed by that leaching with just water, and or else dilute acids, etc., are being practiced. And in fact, actually in our laboratory also, hydrometallurgy section has been tried these processes, and efficiency what it shows varying between 85 to say almost about 90% efficiency. And yeah, lithium will be recovered in the form of lithium sulfate or lithium carbonate, hydroxide, etc. With chlorination, it will be recovered as a lithium chloride. And yeah, hydrometallurgical route, mainly the conversion of alpha to beta spodumene with acid leaching. Before that, this conversion will be made with high temperature again applications, and after conversion to beta spodumene, it will be subjected to different acids. Alkali leaching, etc., are also some researchers have been tried. And in our institute only, Dr. Nilotpala Pradhan is trying to do a couple of oil leaching experiments to recover the lithium from spodumene concentrate. Yeah, this is some information, general information, what is available in the Kings Mountain operations, United States. They crush the ore subjected to ball mill, followed by classification, and the feed will be containing about 1.6 percentage Li2 content, and the final concentrate follow, say the flotation cells are there actually. The hydrocyclone underflow will be subjected to rougher flotation followed by two-stage cleaners, and the cleaner concentrate will be having about 6.3 percentage Li2 content, and recovery of lithium values are around 93.5 percentage. Of course, actually, a couple of examples from the green bushes operations in Australia. Here, the feed is containing about 4% Li2 content, and it will be again subjected to size reduction following a ball mill. And here actually they are operating a bit coarse size, around 250 microns, will be subjected to magnetic suppression. Magnetic impurities will be removed, and the spodumene concentrate, whatever they are hitting in the magnetic separator, it will be used for a say glass grade spodumene, it is called. And the fines fraction, what it is having about minus 250 microns, will be subjected to a cyclone followed by a two-stage again flotation, gravity concentration, and magnetic suppression. Here the non-mag fraction what we are getting is called high grade spodumene concentrate, and the byproducts in these green bushes are castrite, tantalite, tourmaline, and iron oxide. And another two examples are with me, especially on Canadian deposit. Bernick Lake lithium operations in Canada. They have the feed content of about 1.4% Li2 content, and it will be subjected to dense medium separator. The heavy fractions will be subjected to a ball mill, and again you can see here uh, the heavy medium concentrate will be recirculated back to the classification section again. The ball mill is in closed circuit with the cyclone. The underflow will be subjected to a gravity separator, and the gravity concentrate is having the tantalum, and the gravity tailing is subjected to again two stages, one stage of rougher, two stages of cleaner flotation cells to get the spodumene concentrate, and ambiclonate is also there along with spodumene. The final concentrate is assaying about 7.25 percentage. Here is the last flow sheet what I am going to show you on Bald Hill lithium operations of Australia. The feed is containing about 1.1% Li2 content, which has been subjected to screening, followed by a double deck screen is there, and trommel. The coarse fraction is subjected to dense medium cyclones, dense medium suppression, and the lighter particles will be rejected. The heavier fractions will be subjected to again TMS separator. The spodumene concentrate in the coarse fraction is being achieved, and the fines fraction is subjected to reflex classifier, followed by fines two stages of DMS separators to achieve the spodumene concentrate again. Yeah, with this small information, I would like to finish my talk. I would like to acknowledge Dr. Nilima Das for the characterization studies, and all my colleagues at CSIR IMMT who are involved in this activity. Also, I would like to thank the director CSIR IMMT for permitting me to present this work. Thank you very much.
Chakravarti,
Yes, sir.
next, what is the procedure?
Yes, sir. Just since we have not received any questions, if you have any questions, you can just request the panelist for those. Otherwise, we can proceed for the vote of thanks.
Okay. Abhilashi, are you there?
Yes, sir.
Abhilash,
Absolutely. Absolutely, sir.
I see your presentation is very excellent. I think a lot of work are done. Can I request you one thing?
Sir.
We have the IEI Springer Series D,
Okay, sir.
my metallurgy and materials processing.
Sir.
Can you give a small technical paper to us?
On
Scopus index, your work. Scopus index.
yeah, we can probably make a state of art kind of compilation of the work and give it. No problem with that.
The Springer Series D, Scopus index journal it is.
Surely. We can definitely try to make an article on this.
I want to know one thing. What is the difference between the lithium ion battery and lithium metal battery? What's the difference?
Okay. Sir, actually, you have got the very basic difference is that when you make lithium ion battery, you are supposed to use a salt of lithium oxide or a hydroxide or carbonate salt to mix it with the other metal salts and coat it on aluminum foil as a cathode.
Okay.
But in lithium metal or lithium air batteries, you have the exact lithium metal as a cathode, and then you have the reaction taking place. That is a difference.
Okay, very good. Shukumarji, are you there?
Sir. Hello, sir. Yeah, I'm here, sir.
Your presentation, mostly gravity concentration is sufficient for recovery of lithium mineral concentration.
Right, sir. Right, sir.
Mutation is not required if we can do, because you have shown all other countries flow sheets also, mostly magnet separation, density separation, or gravity concentration. This is the showing that one. In our work also, 23% zinc content 4% lithium. Zinc weight percentage is around 23%, and lithium is a 4% lithium we got. But we are not achieved. But we are not achieved by any of the gravity concentration or mutation, that weight recovery. So that to be seen practically what you see in the spiral concentration or wherever it's possible, but we concentrate much on that. So your work also highly appreciable, and you can also do your paper for the publication of our Springer Series D Scopus index.
Yeah, thank you, sir. Yeah.
With this, I request our secretary to give vote of thanks.
Good evening, everybody. I am very much thankful to our President, Engineer Narendra Singh, and I am thankful to my Central Chairman, Dr. Cathode Kumar Rao, and Moderator, Dr. R. Bhima Rao, who is also a committee member and past chairman of our center. And finally, I am thankful to Dr. Abhilash, Dr. Shiv Kumar, and Mr. Tanmay Chakravarti, Assistant Director Technical, who has supported us a lot for this webinar. And we hope that we will organize in physical mode in next years to come after pandemic is over. Thank you all. Good evening. Thank you, Tanmay ji.
Thank you, sir.
Thank you,
Yeah,
sir.
thank you.
Uh, just for the attendees, if you have any questions, you can mail to us at the rate